Everyone. In this video, we're going to talk about section 10.1 in graph, trail, paths, and circuits. So first, let's define what is a graph. A graph consists of two sets, a non-empty set B of vertices or nodes, and a second set that is called E from edges, where each of the edge is going to connect two vertices. So one example here is this graph. For this graph, we have three nodes. We have the nodes U, B, and W, and we have the edges that are connecting each of them. So notice that we can create an edge in notation by getting together two nodes like U and B, B and W, U and W, representing this edge. So this is the edge UB, this will be the edge BW, and this will be the edge UW. Now, some key vocabulary here is that we can say that two vertices are adjacent if there's an edge that's connecting them. And the degree of a particular vertex is the number of edges that are incident to it. So, for example, of the nodes here are going to have degree 2 since they all have two edges coming out of it or incident to it. Now, let's see some graph examples. Here we have a path. We have four vertices or nodes, and we have three edges connecting them between A and B, between B and C, and between C and D. We have here a cycle with 5 nodes and 5 edges, or 5 vertices and 5 edges. We have K4 complete, where we have 4 nodes, and every node of them is connected with each other. You can see that the node A is connected to D, to B, to C with a particular edge, and it repeats with all the other nodes. We also have disconnected graphs like this. For example, here we have 5 nodes, but there are only 3 components connected. A is connected to B, C is connected to D, and E is in isolation. Okay, so we have 3 components. Now in K4, every vertex is going to have degree 3 since it has 3 incident edges. And C5 here, every vertex is going to have degree 2. And this one here, everyone is going to have degree 1. And here, everyone also has degree 1 except for E that has degree 0. Now let's talk about walks, paths, and trails. So if we take a graph G and B and W are vertices in G, a walk from B to W is an alternating sequence of adjacent vertices and edges. So let's see some definitions with respect to this. So let's, if we think about refining the walk concept, a repeat edge is a law for a walk. A repeat vertex is a law on the walk, but it must not be close. If I have a trail, then I cannot have repeated edges, although I can have repeated vertices, and it cannot be close. In a path, I cannot have repetitions between either edges or vertices, and it cannot be close either. A close walk, though, allows for repeated edges, repeated vertex, and of course it's got to be close since it's close. In a circuit, we don't repeat edges, we can repeat vertex, and it must be close. In a simple circuit, we don't repeat edges, and the only repeated edges is going to be the first one and the last one. So pretty much the point where we start is the point where we finish. And that'll be a simple circuit. So the key pattern here is that each concept is going to add one more restriction to the previous stuff. So let's see an example here. So let's consider this graph with 4 nodes, nodes B1, B2, B3, B4, and edges E1, E2, E3, E4, and E5. So let's classify each of these walks. So we have the B1, B2, B3, B1. So pretty much we go from B1 to B2, then to B3, and then we return to B1. This is a circuit, and it is simple, as B1 is the first and the last node. It appears only once. Now we do B1, then B2, then B4, and then B3 and B2. This is a trail. We don't repeat edge, notice. We go from B1 to B2, from B2 to B4, from B4 to B3, and from B3 to B2. So we're not repeating edge, but we do repeat a node. It's not a path because B2 repeats. Now, if we do B1, B2, B3, B4, which is B1, B2, B3, B4, so we're doing a zigzag here. This is a path because it has no repeated edge or vertex. Notice that it's very important to remember all this definition and all these conditions because that will help you to classify and understand what is each of these particular walks. Now let's talk about connectedness. So a graph is connected if for every pair of vertices B and W, there's always going to be a walk from B to W. A connected component is a maximal connected subgraph of G. So for example, this is connected here. We have A, B, and C. Every other vertex is reachable from the other. Now here we have this connected graph with two components because we have A is joined to B and C is joined to D, but we don't have any joining between these nodes with this node. So there's no walk from A or B to C or D. Now, if G is connected, any two vertices can be connected by a path, not just a walk. Now let's talk about the next Euler circuit. So an Euler circuit for a graph G is going to be a circuit that uses every vertex at least once and every edge at least once. So a graph, one of the important theorems with this is that a graph is going to have an Euler circuit if and only if the graph is connected and every vertex G has a positive even degree. Okay, why even degree? So this will mean that every time that the circuit passes through a vertex is using two edges, one to go in, one to go out. So that's guaranteeing that is not going to is not going to use more resources that it needs. So for the start and the end vertex, the first departure and the final return also are going to pair up. So one example of Euler circuit will be considered this. So we have this closed circuit, clearly. It's a closed circuit here. And all the nodes has degree 2 because they have two adjacent edges. They're connected. So by theorem, it means that there's an Euler circuit here. Now, what is the Euler circuit? Well, it's going to be this path. From A, we go to B, then we go to C, then we go to D, then we go to E, then we go to C, and then we go to A. So it uses all edges exactly once. From here to here, from here to here, from here to here, from here to here, go back, go back. So only uses all edges once. Now let's talk about the Cunningham bridge problem. So the idea is, if we have a graph like this, can we cross every bridge exactly once and return to the start? And so in this case here, we have that the degree of A is 3, the degree of C is 3, the degree of B is 5, and the degree of D is 3. So all vertices have a degree. By the Euler circuit theorem, no Euler circuit is going to exist in this case. So the walk that Euler was looking here was impossible, at least in this graph. Now let's talk about Euler trails. So an Euler trail from B to W, with B of course being different from W, is a sequence that is going to start at the node B and is going to end up at the node W, and it's going to traverse every edge exactly once. So a corollary here of the Euler trail criterion is going to be an Euler trail from B to W is going to exist if the graph is connected, B and W have both odd degree, and all the other vertices have positive even degree. So exactly 2 odd degrees vertices means that the trail must start at one and end at the other. The Euler circuit is going to be the special case where B is going to be equals to W. Now let's see an example. For this graph that we have over here, we have that the degree of A is 3, the degree of B is 3, the degree of C is 2, the degree of D is 2, and the degree of E is 4. Here we have exactly 2 odd degree vertices, which is A and B. The graph is connected, so we have guaranteed that a Euler trail from A to B is going to exist. The Euler trail from A to B is going to go from A to D, then D to E, E to C, C to V, B to A to E, and E to V. Notice that this is going to use all 7 edges exactly once. Once again, let's go over the edges. A to D, D to E, E to C, C to V, B to A to E, and E to V. All edges use it once. Now, the final type of circuit is going to be the Hamiltonian circuit. A Hamiltonian circuit, similar to the Euler, is going to be a simple circuit that includes every vertex exactly once. So the Euler was every edge. Now the Hamiltonian is going to be every vertex. So here the comparison of Euler versus Hamiltonian. In the Euler, we must visit every edge once. In the Hamiltonian, we must visit every vertex once. We have a clean theorem for the Euler's circuit, but for the Hamiltonian, we don't really have a simple criterion that we can use. We do have a necessary condition, and if G has some Hamiltonian circuit, then G is going to have a subgraph H where every vertex of G is in H. H is going to be connected, and every vertex of H is going to have degree 2. Now let's see an example of Hamiltonian circuit. So in here we have a new graph. We have A, B, C, and D. They have degree 3, and we have E that has degree 4. Notice that we need a simple circuit that visits every vertex exactly once. So we're going to go from A to V, B to C, C to E, E to D, and D to A. So this is visiting all vertices exactly once and completing the circuit. Now we can show also that no Hamiltonian circuit exists. For example, for this graph here, we have that the degree of A is 2. So both edges A to B and A to E must be in H. The degree of E is also 2, so E and A and E and B is also must be in H. And the edges A to V and B to E are both forces into H. So this gives that the degree of B is equals 2, and it must be in H already. But now C and D are only connected to the rest of the graph through B. So the circuit must pass through B again. So the degree of B is going to be bigger than 2 in H. So there's not going to be a valid subgraph that exists, and we don't have a Hamiltonian circuit. Now, to end up, let's talk about the traveling salesman problem. The traveling salesman problem is, or TSP, is given a weighted complete graph between cities with distances, we can find a Hamiltonian circuit that is going to have minimum total weight. The weights, once again, are the distance. So one small example here will be, let's say we have cities A, B, C, and D, and we want to list all the Hamiltonian circuit starting at A. And so we can go with the route A, go to B, to C, to D, and then back to A. The distance between A and B is 30. The distance between B and C is 30. The distance between C and D is 25. And the distance between D and A is 40. That route is gonna give me a total distance of 125. Now, if I take a different route, going from A to B, then from B to D, and then from D to C and to A, that's going to give me a distance of 30 plus 35 plus 25 plus 50, and it's going to be 140. And then let's consider another route where I go from A to C, from C to V, B to D, and D to A, where they have distance from A to C is 50, from C to B is 30, from B to D is 35, and from D to A is 40. Notice that that's going to give me a distance of 155. Now, the minimum of all these routes is going to be the 125 initial route. So that'll be the best possible that we can get. If we want to try this for large graph, this is going to be kind of difficult to make because we can have n minus 1 factorial over 2 circuit for n cities. So this is a lot of possible combinations, and it becomes difficult to make this same type of calculations. Now, in summary, we have defined key concept of graph theory. We've defined walk, and we have trails and path. Each is going to add a no repetition restriction. We have the Euler circuit that uses every edge exactly once in a closed walk, is connected, plus all the vertices have even degree. We have the Euler trail that it goes from B to W, with B being different from W, is going to be connected, and B and W have odd degree. All others are going to be even. We have the Hamiltonian circuit that visits every vertex at least once in a simple circuit. There's no clean if criteria here. There must be a reason case by case when we're trying to figure out if we have a Hamiltonian circuit. We have the traveling salesman problem with we're looking for a Hamiltonian circuit of minimum weight or minimum distance, and it only works in brute force for small graphs when we're trying to do it by hand. Some common mistakes to avoid when we're dealing with this type of graph: be very careful not confusing Euler with Hamiltonians. Eulers visit every edge once, and Hamiltonian visit every vertex once. They are independent. A graph can have both or neither, or one. Applying the even degree theorem is something that only can be done to Euler circuit, not to Hamiltonian circuit. So be very careful not to commit that mistake. And don't forget the connected condition on the Euler criterion. Also, be very careful on counting edges versus vertices when you're verifying a circuit. You usually want to check both. Euler uses all edges, Hamiltonian visits all vertices. Okay, in our next section, we're going to check matrix representation for graphs.